All right, so we are going to finish up talking about modular arithmetic. Last time we introduced a lot of very important stuff. Now we are going to talk about negative numbers. We talked all about positive numbers last time, so can we do negative numbers in modular arithmetic? And short answer is yes, we can. And it's done actually exactly the same way. If you want to figure out what a negative number is, mod, say, 7, you ask how far above it is from the nearest multiple of 7. All right, so as with everything we've done so far, let's work on an example. Say negative 20 mod 7. All right, and so we ask the question, how far away is it from a multiple of 7? And we want to look at the nearest multiple of 7 that is below it, that's smaller than it. Well, remember, when you're in negative numbers, smaller than it means more negative. So the closest multiple of 7 that's smaller than negative 20 is in fact negative 21. So how far away is negative 20 from negative 21? 1 unit away. So negative 20 mod 7 is going to be 1. Okay. We could do, let's see, negative 12 mod 7. All right, well, negative 12 mod 7, the closest multiple of 7 that's below it is negative 14. That is 2 units away. All right, so negative 12 mod 7 is 2. All right, and so we do the exact same thing that we were doing before. All right, and so now we can subtract because we've got negative numbers. All right, negative numbers, subtracting is really just adding a positive number and a negative number. So 8 minus 20 mod 7. All right, let's look at an example. Well, as before, we have two different ways of doing this. We could just calculate 8 minus 20, that's negative 12 mod 7. And we already know that that is 2. All right, yay, we're done. But we can also look at this and convert the 8 and the negative 20. Well, we know that 8 minus 20, that's the same as 8 plus negative 20. So we can convert the 8 and the negative 20 into what they are mod 7. Well, 8 is 1 above a multiple of 7, so that's 1. We already figured out that negative 20 is 1 mod 7. All right, so 1 plus 1 mod 7. All right. That's going to give us 2 mod 7, which is just 2. All right, and so the beauty is they're equal. All right, they are the same thing. All right, just like we would hope mathematics would be. It would be consistent. All right, what about multiplication? All works the same way, okay? Multiplication exists and it works exactly like you would expect it to. So let's just ask a question. What is 7 times any integer we want? Mod 7. All right, just think about this for a sec. Pause the video. Okay. Answer? 0. All right, because 7 times any integer is always going to be a multiple of 7. And therefore, it's always going to be 0 units away from a multiple of 7. So the 7 times anything mod 7 is always going to be 0. Let's take a look at a different example. Let's look at mod 4, and we're going to multiply everything in mod 4 by 2. All right, so remember, mod 4, the only numbers that really exist are 0, 1, 2, and 3. Any other number, when you do mod 4, is really just going to get reduced down to one of these numbers. So let's just multiply all 4 of these numbers by 2. All right, so 2 times 0, mod 4. All right, this is going to be 0. All right, and this is one of the beautiful things of modular arithmetic is it keeps some of the basic ideas that you really want to be true. If you multiply anything by 0, you really want to get 0 out, or else your brain might break. So anything times 0 in modular arithmetic is always going to be 0. What about 2 times 1? All right, well, this is 2 mod 4, which is just 2. All right, so that's easy. 2 times 2 mod 4. Well, that's going to be 4 mod 4, which is 0, because 4 is a multiple of 4. Okay? 2 times 3 mod 4. That's going to be 6 mod 4. All right, and 6 is 2 units away from 4. All right, the nearest multiple of 4 below it. So this is going to be 2. And that's really all you get. All right, so 2 times anything is only ever going to give you 2 or 0. All right, you can't ever get 3, you can't ever get 1 out of that. Okay? So multiplication has some weird properties, and we've already seen one in this example. Let's take this one right here. What this says is that 2 squared mod 4 is 0. Regular numbers don't work this way. The only way to get 0 with regular numbers is to multiply by 0. In modular arithmetic, there's now a whole bunch of different ways of getting 0. All right? And this is one of them. You can square 2. And mod 4, that will give you the number 0. So modular arithmetic has some interesting properties, to be sure. We're not going to get into most of them. Unfortunately, we just don't have the time, and that's not what this class is about. But if you're interested, start taking some math classes, because there's some really cool things about modular arithmetic. All right, and we're going to talk about the last one here, which is division. All right, and division is probably the weirdest of all of them. And the short answer is division doesn't quite work the way you expect it to, okay? So let's talk about division in general. How do we use division? Well, one of the ways that we use division is when we're solving a math problem. Okay? We want to divide both sides by 2 in this, right? And the reason we want to divide both sides by 2 is to get the 2 to go away. All right? And what do we mean by go away? Well, really what we're talking about is we want to turn that 2 into a 1 so that it is basically not there anymore. So what we're looking for is we are looking for a number such that 2 times that number is equal to 1. All right, and that's really what we're talking about with division. And of course, with normal arithmetic, that number is 1/2. All right, and so what we're doing here is 1 divided by 2 gives us that special number 1/2, such that when I multiply it by 2, I end up with 1. So how does that work in modular arithmetic? Well, we just looked at 2 times everything, mod 4. All right, we just did all of these. We got all of our answers here. And the one thing to look at is we never got 1. So what that means is there is no equivalent to 1/2 in mod 4. There is absolutely nothing you can multiply 2 by so that you end up getting 1. So that means that if you're trying to solve this equation, mod 4, there's really no way of getting rid of that 2. We're going to go into this a little more detail later on, but that's weird, right? That's not what you would expect. Here's something else that you might not expect. 3 times 3 mod 4. All right, well, this is 9 mod 4, all right? Well, 9 is 1 above 8. So this is 1. So what this means, sort of, is that 3 is sort of equal to 1/3 mod 4. All right, 3 is sort of the equivalent of 1/3 when you're dealing in mod 4. And this is not the way we talk about it. And like I said, we'll get into more detail later on. But the point I'm trying to make right now is that division in modular arithmetic is weird and complicated, not what you would expect. Okay? All right, but for right now, I actually want to turn our attention back to the shift cipher. Because the reason we're doing all of this is to be able to take our ciphers and talk about them in terms of numbers and not just letters. So let's write out our alphabet. E, F, G, H, I, J, K, ... O, P, Q, R, S, T, U, V, W, X, Y, and Z. All right. And so let's say that we have a shift key of 2. All right, so we're going to take all these letters and shift them over by 2. So it's going to be C, D, E, F, G, H, I, J, K, L, M, P, Q, R, S, T, U, V, W, X, Y, Z, A, B. So here's something interesting that we noted, is that things have kind of shifted around a little bit. And this is similar to modular arithmetic where the numbers wrap around. And so what we are going to do is for every letter, we are going to associate a number with it. So for A, that's going to get the number 0. B gets the number 1. C gets 2. So on and so forth. All right, until we get down here and X is 23, Y is 24, and Z is 25. All right, and so the shifted version, same letter or same numbers, so C is still 2, D is still 3. All right, da 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 da. 23, 24, 25, 0, 1. And so in order to get the ciphertext, we're going to write the plain text as a sequence of numbers. And to get the ciphertext, what we're actually going to do is we are just simply going to add the shift key to that list of numbers. But we're going to do it mod 26 so that we can then wrap around the end of the alphabet. All right, so let's do an example. Okay, let's say we want to take the letter I and encrypt it. All right, we already know that's going to be okay. Okay, we know that's going to be okay, but let's try and do it our way. All right, so the letter I, all right, that is the number 8. And the way that we encrypt it is we add 2 mod 26 because there are 26 letters in our alphabet. So 8 plus 2 mod 26, that's 10 mod 26, which is really just 10 because we don't have to do any wrapping. And 10, all right, so I corresponds to 8, 10 corresponds to K. All right, so why are we doing this? This seems unnecessary. Well, what if we're taking Y? All right, Y gets mapped to A. Okay, so Y is the number 24. Let's add 2 to it. Mod 26. This gives us 26. Mod 26, that's 26 is 0 units away from a multiple of 26. That's going to give us 0. And 0 is the letter A. All right, so that through very quick mathematics allows us to figure out what each letter is associated with from plain text to ciphertext. Right? This allows very quick calculations to try and figure out how to change a plain text into a ciphertext and back again, because in order to go back, what do you have to do? All right, we added the shift key to encrypt our message. To decrypt our message, we will just subtract the shift key. And this is what computers are great at, right? This is why computers were made, to add and subtract, essentially. Really just to add, but that's a whole new thing. And so something to note is that the shift cipher is also sometimes called the additive cipher. And this is why, because really all we're doing is we're just adding a number to every single letter. And so just one more example. Let's say we want to take the message 2. All right, well, this would be represented by the numbers 19, 22, and 14. All right, let's make our shift key 5. All right, so we're going to add 5 to each of these. Mod 26. All right, so when we add 5 to all of these, we're going to get 24. 1, because 22 plus 5 is 27. Mod 26 gives us 1. And 19. The letters for this is going to be Y, B, T. All right, so when we do our encryption, 2 gets encrypted into the message YBT. And to decrypt it, we would just subtract 2 from all of these, and we would end up with our original plain text message. So this may still seem like it's a lot of work to do something that is pretty simple to do just by looking at things. The next cipher that we're going to talk about, the affine cipher, is going to demonstrate why we need this new form of arithmetic, because we're going to combine not just adding a shift key, but also multiplying by a different key. All right, so we'll talk about that in our next video.